discuss with him, and we look forward to getting some added stimulus for the discussion.
Okay, thanks, Markus. Thanks for having me, and it's a great pleasure. It's some time ago I was here last, but I don't exactly know when it was. It was from Zurich, I think. I was here last time. So yes, Markus alluded to a new grant we have from the Novo Nordisk Foundation that is called the Center for Quantum for Life. So we want to show that quantum computing can benefit the life sciences in different ways, and the connection is quantum simulation to show and of course not do everything at once, but to show proof of principle concepts that could help understanding computational problems that appear in the life sciences, as for instance the docking of molecules in which quantum processes are involved. But I hope the center is starting now, and we're hiring, and if you know someone who could be interested to join the team, let me know or bring them in touch. Apart from that, stay tuned for the results. I thought here now I want to bring the focus back to something that is sort of like very close to my heart. That's quantum communication, and I think that also is it's a piece of rather theoretical work, but I firmly believe that it's rooted in an idea on imperfections of hardware, and I very much hope maybe that will lead one day to actually being implemented in practice, maybe even in space. Let me tell you that story. It's a joint work with Alexander Müller-Hermes, who in the meantime moved from Copenhagen to do a postdoc in Lyon, and now actually got a faculty position in Oslo. And our work is on the archive from last year. And I want to also point out Paula Belzig, who is in the audience and who is working with Alex and me on this project. And we're just working on it and trying to write a new paper on this topic. So stay tuned for that as well. Okay. So if there are any questions, feel free to just interrupt me. I think it's going to be taped and everything, but I hope that doesn't hold you back from asking questions. Okay. So what is communication? So the communication setup is really the one from Claude Shannon from 1940s. We have an input, and I even have a laser pointer. So we have input bits, and then what we can do is we can encode the input bits and send them over a channel, maybe a very noisy channel. And then we build a decoder that decodes the signal, and we hope to receive an output that is really close or identical to the input. That's the basic setup. And now you may say, well, why do I have to use many of these channels just once? I could also imagine that, and if you restructure the diagram a little bit, that you use one particular channel, but you use it many times. Okay? So you prepare a code word, and then you send it over that channel once, the first part of it, and then the second part, and so on. But that's sort of like the way of depicting also that serial sending. Is that okay? Okay. Now I need to introduce some notation. So I have m input bits. I have n uses of the channel. And what do we want to do? We want to find the capacity of the channel. And that's a very long formula. But at the heart of it is the ratio of m divided by n. So I want to maximize, or take a supremum, a maximum over m divided by n, such that the input and the output are identical. Okay? Up to some error epsilon, so it means with probability 1 minus epsilon, they're identical. So at most with probability epsilon, they actually may differ. And then I want to look in the large n limit, so I want to look at many channels. I'm happy with a small error epsilon, but I want to keep the error small. So you can think of epsilon at 10 to the minus 5 or 10 to the minus 10. And so I want to basically look at epsilon going to 0. But I'm first taking the limit n to infinity. So I'm happy to tolerate a small error. This is this scenario from Claude Shannon from the 1940s that really revolutionized the way of how we think about communication. And he even derived a formula. So that's a rate. It actually has a formula that you can evaluate. So if you're given a channel, you can evaluate the maximum over the mutual information of x and y, and you maximize over interdistributions. But that's not so relevant for us what the exact formula is. And it involves, of course, the Shannon entropy and so on. But the actual formula is not so important for the remainder of the talk. Okay, so now what changes when we go to quantum communication? Actually, nothing really changes. It's the same setup. All that changes is now that the channel is a quantum channel, and because the quantum channel might have a quantum output, we have a decoder that's a quantum machine. And also the encoder, of course, if it's a quantum channel, we allow this to be a quantum machine. But we fix for the moment, we keep the input bit still classical, and we keep the output bit still classical. We could change that, and we could make quantum out of that and discuss that, but it will make the whole setup somewhat more complicated, and at the heart of the story is really already, this setup is at the heart of the story, and I want to just keep it with that scenario. But feel free to ask later about the quantum setup. This is known, this type of capacity in this setup is known as the classical capacity of the quantum channel. Classical capacity because I'm still looking at classical bits I want to send, but now it's the quantum channel. Okay? This is a scenario Alexander Holevo started studying in the 1960s, and quite remarkably, together with Schumacher and Westmoreland, we have this HSW theorem, the Holevo-Schumacher-Westmoreland theorem, which basically says that we have just a very similar formula to the one that that Shannon derived. It's just that we have to swap out the entropy to phenomenon entropies. We have to do some quantum optimization, and then we have to add something maybe a little bit nasty that's called a regularization. But never mind, again, we should not focus so much for the remainder of the talk on these issues. Okay, so that's the setup we're going to play with. Here's a small observation, and no one really protested, but I think that this assumption of having a noiseless encoder and decoder is actually very unrealistic. It is realistic in the classical case. And why is it realistic? It's because your phone, when it communicates with your router, for instance, it actually is faced with that problem. It has this noisy communication channel, but your phone essentially does everything noiseless, and the router also is a computer that acts noiselessly on the data. But in the quantum case, that is not the case and will not be the case, and people believe that it will not be the case even in the long-term future. Okay? We don't know what happens there, but at the moment, people believe that the realistic setup will involve errors happening on the gates in between. And so this setup with noiseless encoder and decoder that people have written big books about might actually not be the one that is realistic. So entirely new problems appear, and if you have actually the quantum capacity, even a very basic question appears, namely, is quantum communication possible at all? Actually, it could be that the answer is no. Now, in this classical setup, it's easy to see that the classical capacity, will be non-zero in non-trivial cases, but certainly what is not clear is if the capacity formula is continuous, meaning that actually if we have a gate error delta and we take this gate error to be small, that actually we approach the noiseless capacity. So the capacity, or what we think the capacity of the channel is, does it really correspond to the actual capacity that we're having? And I think this is one of the fundamental open questions here that appears in the setup. So are there any questions at this point? I will explain more in detail what I mean by the concepts, but maybe there are questions at this point to the setup. No? Okay. So now, of course, your reflex maybe says, oh, well, but isn't there fault-tolerant quantum computing? And yes, there is. It's a highly developed field. It's a very complicated field. And of course, a lot of people are working in it right now because it's so relevant with the hardware that's coming online. So isn't this problem already solved in some way? So in fault-tolerant quantum computing, we have an input, we have an output, and we have a computation. And there is tools available to encode the computation in such a way that actually I can get the answer. So if I want to factor some large number that comes in as my input, and I want to get the prime factors out, the 2 prime factors out, I can run Shor's algorithm in some encoded space so that I actually get the correct prime factors out. Okay? So that is a scenario, and we have the tools available, and there is a so-called threshold theorem that covers this. But what you should keep in mind is that in their setup, the input is actually classical. So it's stable classical information. Like in Shor's algorithm, you get the big number n, and the output is also classical, namely the 2 prime factors, p and q. Now in our setup, the situation is a little bit different. And we get the input, but now our encoded computation that we want to encode actually, well, it still has a classical input. I might have made our life easy, but the output has to be quantum because we're going to feed it into a quantum channel. Likewise, for the, here it should say decoder, sorry. For the encoded decoder, we have a quantum input and we get a classical output. So is there some kind of easy fix for this? Well, I mean, you could say, well, maybe what I could just do is I could just do everything in the logical space and I could send like logical qubits across the channel. Yes.
Fix for what?
Oh, a fix for the fact that, so this is the this is fault tolerant quantum computing, the setup people have studied. Yeah, the fix for the fact that here we have a quantum input. So we cannot, you see, we cannot use the paradigm from the left here, right?
But why can't you at least try to just map your encoder channel plus decoder onto the encoded computation? Couldn't it be that it just exists a one-to-one map?
Yeah, that's true. So you mean I could regard the entire thing here as the encoded computation. But you see, the gate error is delta, right? But I want to, and delta is very small. But I want to keep the channel as an arbitrary channel. So the channel is say a 10% noisy channel, is something above the threshold. Okay, so this whole thing here cannot be regarded as an encoded computation with an error.
Okay, thanks.
Yes?
A very neat question. So is there a reason why the channels are like a tensor product, so we have different copies of the same channel, or why wouldn't we have a big one?
Oh, one big channel. This is a standard scenario. I mean, we can always talk about making the setup more complicated later, but the very standard scenario already displays the problem. But yes, I mean, in principle, we could look at more general things. But with correlated noise, it gets very difficult to encode. Okay, but very good point. And so let's see if there are other fixes, right? So one fix would be like, okay, why don't we encode the entire computation? We have logical qubits. We do everything in a logical space, and we try to send them across the channel. But you see, if I have a logical qubit, then of course it has like it's represented by tons, maybe dozens, maybe thousands of physical qubits. They will not fit into this here in some sense, right? I will not get them across. So I have to like somehow encode them, or so I say like naively that doesn't fit the channel. Okay, I have to push a physical qubit through and not a logical one. Another thing, and that is essentially what we're doing, is what you could do is you could take the logical ones and you could decode the logical ones here, and then have physical qubits, but note that somehow in the decoding process there's noise coming on them. And then of course it doesn't fit anymore. Like the channel code word will not fit, it will have noise on it. It will not be the channel code word anymore for that channel. Okay, so we have to combine, it will have to combine the techniques now. Okay? So we have to somehow play at the interplay of communication theory and fault tolerance theory. That's sort of like the thing. All right. So here's the plan. I want to tell you about error correction and fault tolerance. I want to introduce formally what I mean by fault tolerant quantum communication. I want to give you a couple of key ideas in the construction, and yeah, and that concludes. So let me get going. So in error correction, what is error correction? Simplest idea in error correction, I think it's very nice to remind ourselves, because it's really kind of cool. So you take a 0, which is classical, right, or a 1, and you encode them in a repetition code. So 0 goes to 0, 0, 0, and 1 goes to 1, 1, 1. Okay, it's very kind of nice, because if one error happens, for instance, on the second bit, then this goes to 0, 1, 0, and 1, 0, 1. Okay, and clearly we can still identify what the original code word was. because we just do majority decoding, which is say where there are more zeros or more ones. More zeros here, that must be a 0. More ones here, that must be 1. Yeah, that's the basic idea. And Peter Shor in 1996, I think, I stole some pictures here from Wiki. He made the code words for a quantum code so that you can protect. So basically, you can digitalize quantum errors so that there are errors on the bit and errors on the phase, so that you do a repetition code twice. You do it for the bits and you do it for the phase, and you see it happening twice here. So you have repetition of this GHZ state, and inside you have a repetition for the phase. Okay, that's kind of nice. So let's see how that looks as an encoding circuit. So if I take my qubit psi here and I encode it into the Shor code, then the Shor code is manufactured in such a way, it's constructed in such a way that if one error happens here, then I can decode this code. Okay, then the decoding brings me back to psi. That's what the Shor code excels in. But now what happens if there is a gate in the encoding or decoding, right? So if now the Hadamard gate has an error, well, what will happen actually is that the error could spread. So it will actually spread because there is these controlled knots. The error will spread over here, and suddenly you have 3 errors here. But the code only protects against 1 error. So bad luck, actually it won't work. So you see that somehow it's an important difference in errors happening in storage, like after I encode it in the code, or them happening in encoding and decoding procedures. So one has to be clever in designing codes, and people of course done that, that are actually robust against errors happening even during encoding. This is sort of one thing. I want to actually point out one more thing, and I don't really know how to say it because it's somehow a trivial point, but it took me a long time to understand. You cannot protect an unprotected qubit. I kind of want to make a point out of that. Because here's another thing that can happen. You are like, okay, great. So I'm doing all of this computation I have to do in this protected, after I put it in a protected subspace, and I have managed to do a nice code where errors don't spread in encoding and decoding. And then, I just want to get my qubits back, so why don't I just decode them, okay? So why will that not work? And the reason is that right at the end, so imagine now, you go through this encoding, you do some computation even here, and then you go through the decoding procedure, and then at the end you want your qubits out. Well, it won't work because right at the last step before you get your qubit, your error might hit. Okay, just at the very end. And you can never avoid that. Okay, so if you want to have a qubit, you need to, and you want it to be protected, you need to keep it somehow in this protected subspace. If you get it out of there right at the last moment, it might be hit by an error, and then, okay? So just keep that in mind. It's sort of like part of the complication of the game here. Even though it really sounds trivial, but if you think about it, try to think about it a little bit. It's sort of surprising. Because sometimes you come up with procedures, and then at the end, Okay. Yes.
Maybe I didn't understand when you say at the very last moment, it's like the last decoding.
Yeah, the last decoding step. Okay, so you get it, and there will be some gate that's the last gate before you get the qubit. Sure. Okay, and that last gate with some probability delta will be hit by error. Okay, there's no way you can protect against that if you want to get it out. Okay, so what is fault-tolerant quantum computing? So in fault-tolerant quantum computing, one of the ways people do it is they take this classical information, then they encode the classical information, then they get this circuit, and then they encode the entire circuit, and then they decode again, and they get an output. And now it's a little bit, now I said, you can't protect the unprotected qubit, but if you think about fault-tolerant quantum computing, the input and the output are assumed to be classical, so they're assumed to be stable or already in an error-correcting code. So this is what allows you to circumvent in normal fault tolerance what I just said before, that you cannot protect. So here somehow you can imagine that the procedure is designed in such a way that that the output's provided already in a code, right? In the classical repetition code. You imagine magnetized area on your hard drive or something, right? That's the last thing that you push it into. So that is in fault-tolerant quantum computing. But that's roughly the setup, okay? You get the input, you encode, then you work in the encoded circuit. Think of Shor, okay? Think of Shor's algorithm, and then decode into your classical information. And regardless of errors happen here, because here it's still assumed to be classical, or if they happen here, right, in the encoding circuit, it's designed, or somewhere in between, it's designed in such a way that errors do not spread. And so you have so many error correction procedures on it that the error correction, while the computation goes on, there is error correction also going on, and the error correction corrects more errors than it self introduces, okay? So it's somehow, you know, a priori it introduces errors, but it corrects more than it introduces, and thereby, you know, the machine keeps working. Now, for our work, we have fixed the noise model and an error model. You've got to do that in this business, otherwise it's too complicated. We fix actually Pauli IID errors with strength delta. We can generalize to other models, but let's not worry about it. It's already kind of like complicated enough. We have IID errors. You could also probably generalize to whatever people do in fault-tolerant quantum computing, but there's many different concepts. So we try to stay with that model, which is sort of like very concrete. Now, how do they do it? So how do we actually encode? How does fault-tolerant computation work? First of all, you have a circuit, you have an encoding machine, you pick some universal gate set, and you know, like X, Y, Z, T, and C naught. But then it's good to also have the other gates, like for instance, like the gate that says prepare a 0 or prepare a 1, to put them explicitly in. And partial trace, and also actually like a gate that measures 0 and 1, okay, to put them in. All right. Then here's your circuit. You write it in a circuit in this way. And then what you do in this construction is you replace every gate by a gadget. So here is an example. So for instance, such a gate here, it will be replaced by a gate that works on the encoded subspace. And we are going to use actually a 7-qubit Steen code. Includes also error correction in this way. So you will always see me replacing one wire by 7 wires. But again, we can do this with other cases too. So every circuit will then be transformed into such a circuit that has 7 times more wires. And then how do we encode into the code? Okay, so there is a procedure for encoding into the code. Here is the 7-qubit Steen code written out. Okay, so it's just a logical thing. You see it actually resembles the Shor code in some ways, but it has fewer components, a little more complicated, so like nicer properties. And then we use gates and gadgets from the Aliferis, Gottesman, and Preskill paper, which is a very nice paper. And then sometimes you may have heard of these transversal gates. These are particularly nice gates, and I want to just highlight that because these are gates that somehow, for instance, if you do a Hadamard gate here, then then doing a Hadamard gate in the logical space just means doing a Hadamard gate on all of the physical wires at the same time. And a similar thing is true for the C naught gate. So it's a very nice, transversal gates are very nice because they help you kind of like understanding what goes on the concrete terms. And then there's a concept that is important for our work, that is concatenation. So one doesn't only do this once, so you do this replacement not once, but then you repeat it, okay? So you repeat it with like L levels. And of course nowadays there are also other ways of encoding into codes, but and for instance surface codes and so on. We chose for this first work on the subject to actually stay with a very rigorous early work by Gottesman, Aliferis, and Preskill, because it allowed us to trace kind of like the steps very rigorously and work with that. So the more you encode, the better the protection, okay? And it's very fast. The protection goes up doubly exponentially fast in the number of levels. And this will allow you then to do this with very little overhead, at least theoretically very little overhead. Okay, decoding works in the same way. And you you concatenate and you decode in the same way. So what does the threshold theorem from Gottesman say? And this is important for us to understand. They basically say that, well, you are interested in carrying out a certain noiseless computation, but it just so happens you don't have a noiseless apparatus. You have a noisy apparatus. So what you do is you do the following construction. You do this encoding here with a number of levels. You have this encoded circuit in the way I've just shown you. And then it says, the theorem says there is a threshold, so there is a delta. Maybe very small, 10 to the minus 6, but let's say it's there, such that if the noise is below that level, then for all circuits and for all inputs, the probability that this situation here differs from the perfect situation is very small. And it's actually small. It's linear in the number of gates. Okay, so it's like a union bound of all of them. And then you have the suppression factor, which is, and now if you, for instance, imagine this delta to be a half, like half of delta 0, then here it will say actually a half. Okay, so it says a half to the 2 to the k, where k is the number of levels. This is, of course, hugely fast suppression. Okay, so that means actually that you only need, a logarithmic amount and even less of blow up in order to combat the number of gates here and get actually an arbitrarily good approximation.
So that's for local and uncorrelated errors?
It's for local uncorrelated errors, yes. But you see the difficulty already arises here. And why? It's because the gates, it means that on the positions of the circuit, right, you have these local uncorrelated errors. But of course, a gate from here will feed into the other gates. So the errors overall will be correlated in the system. So the gates, like on the qubits, right, they will be correlated, even though on the positions now we assume IID. Now this work has been generalized, and you can assume that these are, as long as they're like exponentially decaying errors, and also for more general noise models, you can do that. And I don't think there is an obstacle of our work to continue to that level, but we started at that point, but absolutely. Okay, so now I can come really to the formal definition of what I mean by fault-tolerant capacity. Okay, so what we are interested in is, well, we are interested in actually, understanding the capacity at, of reaching the capacity at zero noise. That was just what we had before, okay? So this is my picture from before. And the maximization here goes over encoder-decoder pairs, where I have m inputs and n channel uses, and I'm looking at just the capacity as we had before. But now what we're having, of course, in the real setup is this, right? So we have errors, and we want to understand the capacity at delta noise, okay? So, and now it's important if you pay a moment attention. So now the delta is fixed, okay? So think of it really as the capacity at delta noise. So think of your favorite delta, maybe 1% or 0.1%, maybe better. Say 0.1% is your favorite delta. You look at the capacity delta noise. So capacity is still a function of the channel and has the same formula as before. Okay, so I still want to maximize m divided by n, number of inputs versus number of channels. I still want input-output to have no errors. I still want n to be large and epsilon going to 0. But now my encoder-decoder have at every gate with probability delta they're being hit by error. So the maximization is now over encoder-decoder pairs, right? But you can think of, well, okay, maybe it's over fault-tolerant codes, and that I'm already kind of like designing this thing so that it can withstand that, okay? So I want to design now encoder-decoder pair that can withstand this noise. And so what is very important is that the noise is not allowed to decrease with growing n, right? You see here that the capacity depends on, that the capacity includes this like, okay, I'm taking this large message limit. Okay? But this delta cannot decrease. So the delta is like fixed. It's like you buy the IBM machine and it has, such and such noise level, okay? Or you build something in your lab and it has such and such noise level per qubit, but now you want to scale up to higher block length, okay, 40,000 qubits, I don't know. So you keep that. Noise is not allowed to decrease. Okay, so is the setup clear? Yeah? Okay, so now comes the theorem, and the theorem is very analogous to the other case, right? So in our case now, these boxes with the arrows, the statement is there is a threshold such that the capacity at delta noise, okay, so which we then construct in a way as you encode, you compute in the encoded case, you decode, you encode again, right? So this is an example of these blue boxes with arrows on it. So the capacity in the delta noise case is actually lower bounded by the capacity in the zero noise case minus a little bit, okay? So the point, of course, the capacity at delta noise case will be smaller than the capacity at zero case, right? Cannot go up if I put noise on it. So this will be smaller than this, but it will not be much smaller, okay? It will just be a little bit smaller. And then there's a few details. Well, one thing that's important is that this fudge function somehow, f of delta, it actually decreases, it goes to 0 as delta goes to 0. Okay, so that means actually that we resurrect the meaning of the capacity at zero noise. Okay, so these capacity formulas like Holevo, Schumacher, Westmoreland, and other capacity formulas, they are the capacities at zero noise, and this now means that even if your encoder, your machine is noisy, actually it still reaches this capacity, minus a little bit. That's the state. Any questions? Yes?
Yeah, so here now this picture on the left suggests that you also decode to a classical bit, but I think it won't be the case, right? To go to a logical space for
yeah, this is now, okay, so you could also now, instead of what is there on the left-hand side, you could think of this one, okay? So we make a construction such that this is the same as this, okay? And now how we do the construction looks like that, okay?
Okay, but kind of the right-going green arrows, they go to quantum systems nevertheless.
These ones here. Yes, this goes to quantum systems, yes. Okay, so, but keep in mind the complication is that you cannot protect the unprotected qubit, so we have to be clever in the design of these objects here that allow us to achieve this.
So you said protected qubits over the channels?
Well, we'll see what we do. Okay, I can try to explain a little bit what we do. Let's see what time it is, okay? I will try to explain. Are there more questions?
So if you vary the channel, say, of a fixed dimension, then you could look at the infimum of the supremum of f delta or so. Does that go to 0? So could I give a uniform bound there?
No, we don't have a uniform bound because of the regularization in these capacities. They actually provide a problem there. Okay, so maybe one day we can do something about it, but for the moment it's like that. I mean, if you have an additive capacity, say if you restrict yourself to degradable channels or something like that, then you're fine. But then it will only depend on the dimension. It will anyway always depend on the dimension of the channel. At least I think it will depend on the dimension always. Yeah, I think that we cannot avoid. But it's true. I mean, it would be nice to do that. There is another statement here that it would also be nice to avoid that the level can depend on n. Okay, so the level, we do these kind of encodings here with these concatenated Steen code. The level also depends on n, right? There's nothing that forbids us doing that, but also would be nice to get rid of that. There are new codes. So we know that we can do fault-tolerant quantum computation with constant overhead. Maybe we can also do that with constant overhead, but we're not there yet. Okay, so we somehow have to do it step by step. Okay, but yes. Okay, good. Here's the proof. Okay, so what's the proof? Proof has two steps. Okay, step one. We somehow. What's step one, right? So you basically want to say, well, this was my big setup. Okay, my idea is that I'm encoding, then I'm doing something in the protected subspace that I'm decoding, right? What I was kind of like told you that was like the difficult thing, and then I'm encoding again, okay? So the idea is to kind of build an effective channel out of this, okay? So that when you have this effective channel, that it looks like this with this effective channel here. Okay, why? Because somehow the idea here is that what comes out of the encoded circuit, these are somehow logical qubits, right? So you want to take these logical qubits and then you want to send them through some kind of effective channel. That would sort of be the idea. And this effective channel, and so this one here somehow morphs into the perfect part here, and this morphs into the perfect part here, and we're left with something that is a little more complicated. Yes?
Maybe the question, so is this completely deterministic? So, I mean, the decoding, encoding, and everything, is it completely deterministic? So if it doesn't measure it, depending on the measure, it does something, or there's nothing like this?
Oh, no, there is error correction. Yes. Yeah, this error correction. Error correction always involves like measuring something and then feeding back the signal, etc. Right? You got to remove the entropy, right? In some sense. Okay, so now the step 2 is I will tell you a little bit more about how to build this effective channel. Whatever it is, okay. The point of step 2 is to show that the effective channel has a similar capacity as this one, as the original one. Yes. Yes.
And then why did the, let's say, pre-processing become this blue perfect box now on the right-hand side?
Yeah. Well, I will tell you more about that. Okay, I want to first, this just for the high level. Okay, so high level, we want to build an effective channel out of the middle part, and then in the second step, we'll show that that effective channel has a similar capacity to the original channel. Okay, and thereby we've shown that what we're actually after has a similar capacity as this one here. Okay, and that was kind of like the statement. Statement of theory, but we'll come to that. Okay. Yeah. So, step 1, single decoder. Okay. Yeah. So this is actually. Let me see if it says here. So think of first think of like a single decoder box. Okay. Think of you now doing this. What I told you, like you're taking the logical qubit, you're unprotecting it. Okay. Then, of course, it's going to be hit at the end by an error with probability delta. Okay, nothing you can do. I mean, that's why I was telling you the story about that. Okay, you can't do anything about it. Now, the point is, though, that actually, that's kind of like the worst case that can happen for you. Okay? Because the protection is exponentially fast, you have basically a doubly exponentially fast sum, and the people from Gdansk, the Hordetskis and Mazurek, they showed actually that the total amount of error here is actually proportional to delta, okay? Constant times delta. So that's okay. So this intuition, right, that you're being hit by an error delta at the end, that's kind of like the right thing to think about it in your head. So it's not worse than that. Now, if you do this now with many channels across, what can happen, though, is a complication, right? So we have many qubits. We want to decode them. Now, what can happen is that, you know, it's all nice, you know, like basically we decode, we get all these perfect things with 1 minus delta, right, probability. But then the noise will actually might be correlated now, okay? So I say, oh, well, it's delta noise, but that noise might be correlated. And actually it will be, that's a little bit of a complication of the part. So there is some non-trivial aspect to that here. I'll say more about that. So how do we construct this effective channel? So let's go to that picture, okay? How do we do that? So the idea is that you insert an ideal encoder. Now imagine I give you this perfect thing. Like I give you a qubit and you can encode it perfectly in an error-correcting code and afterwards perfectly decode it. Okay, there's no errors happening. Then of course that's just the identity. Okay, so or here it's shown the other way around. Okay, so you have this perfect qubit, logical qubit, or you have your logical qubit, right? You decode it, then what you get is an error syndrome, right? And you get your physical qubit, and if you feed the same error syndrome and encode back, you actually get the same qubit here, right? So this would be an identity map. And so we insert that identity map everywhere, here, and we also insert it here. Okay. Now, And now, see if that comes out nicely. And now, now the theory of fault tolerance tells you that if you have these noise, so that if you encode something and then you code, and you encoded your encoding operation or your quantum computation, and then later you have a perfect decoder, okay? Then actually the entire thing looks like your perfect computation that you've done. Okay, so the only problem before was that when we decoded with these things that could have errors in there. Okay? So if we just pretend the errors are not there, then actually the theory of fault tolerance will tell you that you get the perfect encoder back. Plus an error syndrome. It's like this error syndrome I showed you from before. Okay, so you get an error syndrome because when you decode, you have some error syndromes. There will be errors happening in the computation. There will be error syndromes, but never mind, right? You have them stored. And now you build the same on the other side. Okay, so let's not worry about that. And now this here is your effective channel. Okay, so your effective channel is actually, this is kind of interesting, it's actually a qubit channel that takes the qubit and codes it perfectly into your error correcting code. Okay, and it feeds an error syndrome. So it puts it into a code subspace corresponding to the error syndrome. Then it decodes the beast. Okay, but during decoding, errors might occur. Then it feeds it into the channel. Then it encodes it again. And then it decodes it with the perfect thing. Okay, that's our effective channel. You see that basically the effective channel is a channel that looks like it's going from a qubit to a qubit, right? It basically undergoes the black box, which is the major source of noise. And from the Hordetsky's, we have the intuition that what happens here is really just a delta noise on top. Okay, so this thing here is kind of like your channel that you want to code over, plus a noise at the start and a noise at the end that's of delta strength. Okay? The only thing that's sort of like really weird is that's going to that the whole thing is, the noise is going to depend on the error syndrome that's going to happen. And this dependence will actually be correlated across the channels. Okay. So we have these boxes. It's all nice IID boxes, but the error syndrome here, which is decoupled from the rest because that's the perfect thing, is actually correlates that noise. And that sort of like gives us a complication. But what you already can see here, and I'm not sure if that's the right way of where I should say it now, okay? What you see from this picture is that now, how do you now design your coding scheme for your thing? The way you design it is that you build this perfect encoder not for the design of this is not for your channel here. The design of this perfect encoder is for the effective channel. Okay? So if you were to ignore and build the perfect encoder for this channel here, it would not work. So you have to build that for the effective channel. That's sort of like the insight in many ways. Okay, so we have that. That's just more pictorially in this way again, that basically the noise here is correlated from the error syndrome, and actually here we have the effective channel, just it traces out the error syndrome, so that's all nice, but this little error, we have to deal with that, and we can deal with that by explicitly working with it. And then you have to do capacity of this effective channel. You use something called the post-selection technique, that will allow you to remove this syndrome, and then you have removed it, and then you're back to the original thing. Then there's still a delta deviation from the capacity, but the capacity formulas by Olivo, Schumer, Westmoreland are continuous in this. So standard random coding actually will actually work there. Yeah, so the resulting Olivo capacity is continuous in delta, then you regularize. There are some complications there, but it's the basic idea. So with this, I think that was sort of what I want to tell you. Maybe the take-home message is really that one of the take-home messages is that you need to now adapt this code, okay? And on the technical side. But let me give you a maybe a summary to why you should care. I think what the interesting thing is here is that it's a new paradigm for fault-tolerant quantum communication, and maybe the people who, and I'd love to speak about people who've thought about quantum repeaters. They have already kind of like thought about certain issues in here, but I don't think have done the formal setup here. I think it's a new paradigm, but I think we define the fault-tolerant capacity, we establish positivity and continuity, also for the quantum capacity. Of course, now, I told you this, right? And when you thought about encoder and decoder, and I've said, oh, here in my wireless router, and maybe from here to the space station and so on, you thought about these large distances. And this, of course, hopefully is one of the applications. But I think it has this broader relevance in quantum computing. And if you think back of superconducting qubits, and I'm not sure if have you ever seen a superconducting qubit? Yeah? You see, the shocking thing about superconducting qubits is that you can see them. Okay? So they're so big that you can see them with your naked eye, right? And your phone has billions of transistors, and you will not be able to see a single transistor. It already tells you that these superconducting qubits, they're so large that they will not fit. Actually, many of them, they won't fit in your phone. 5 billion of them will not fit in your phone. And they will not fit in this fridge either. So what you might have to do is connect fridges. Right? So you have connect fridges, and then, of course, they have to communicate. So I think you should also think of this scenario as like connecting fridges, connecting small cores of quantum computers, and the question of how do we do this? How do we design the things? Because we have these noisy quantum computers, now we connect them with even noisier lines. How are we combining these codes? And this code combining business, I think, is going to be here to stay. So with this, I want to thank you for the attention. In Copenhagen, we have our QMath Center, and it's going to be expanded now. There's Paula on the very right. This was our recent outing after Corona was over, and it was very nice to get all of us together. And we were standing there, and then we were also trying to jump. Now, I'm not sure if you should look at individuals, but it's fun to explore them, of how they're actually jumping. Anyway, so maybe we go back to that. Thanks for your attention.
Thanks a lot, Matthias. Further questions? Go ahead.
No, I was thinking.
We were thinking manually. So I'm wondering, this is all for qubits, no? The construction. No? Is it general? So
Yeah, it's general.
So this also holds basically also for higher dimensional quantum systems.
Yes. I mean, yes. I mean, for the channels, yeah. If your physical channels yeah. So if your physical channel is high dimensional, you can just embed it into qubit space, and then use the theory there. Yes.
And for the error correction.
Yes. I mean, if you now have a specific scheme in mind, we would have to look at that specific scheme. Okay. So if you now say, well, okay, so I'm using a error correcting code for Q trits, and I want to build a fault-tolerant architecture on top of that, etc. I think in general, this is sort of like the question of how do I combine codes now? Okay, how do I combine a communication code? So I want to communicate over a certain channel, and I have some communication code, and then I have some code in which I want to do my computation. The question somehow is, how do I combine them? In what ways exist? And for us, this is proof of principle. It's possible in some way, but it would be nice, yeah. So.
I guess from a more operational standpoint, the question is, what is the most efficient way of doing it? So it might
Yes.
be that I can get the same solutions as you say.
Yes.
But maybe using trits instead of bits, qubits.
Yes.
Qubits might be a much more
Yes.
efficient way of implementing.
Yes, absolutely. I think this is certainly not the most efficient way of doing it. Okay, it's a way that we could show works. Okay, if you want to go further and if you have some specific scheme in mind from a practical point of view, then we need to look at that. But even from a theoretical point of view also, right? I mentioned these constant codes. I mentioned also the surface codes. You know, like there's certain like areas which should explore. And then, of course, another one maybe, you know, how do we go from stationary qubits to, you know, continuous variable communication? You know, maybe if we think this, you know, if we think superconducting qubits, then microwave mode. So yeah, there's a multitude of questions. But if you think of angular momentum, is that what you're now thinking about? Yes. Yes, it would be nice. I mean, I guess I guess the first question is: do you have a system in which you already explored some code words that are quantum code words? Right? I think that would be the first thing. And by the way, maybe this people have done, right? So these attenuated pulses or other. Have you explored like yeah? Yeah, and from that, I think it would be nice to put something on top there.
Everyone else seems happy, hungry, or
So the F, so you showed like it's the difference between the noisy
Yes.
version and the perfect version. You have this difference F. What is it again?
Oh, it's just, I mean, I just told you that it's a function that goes to 0 with delta going to 0. I mean, it depends on various quantities, right? So, for instance, continuity of entropy. Right. So it's terms that you should think of relate mostly to continuity of entropy. But it would be nice to get stronger results, I mean, in this direction. But
Then I guess it also depends on the concrete model.
it also depends on the concrete model. Yeah, that was a little bit under the hood, right? So even the definition of fault-tolerant capacity, of course, depends on, for instance, the gate set that you choose to write your circuit in, right? So there is a way of now writing the circuit, and so in principle, you should optimize over like the, you know, you optimize over the gate set, right? In some sense. So we chose now a gate set in order to show, right? Because we show a lower bound, we can just pick a gate set of our choice for which we can do it. Yeah. But yes. Yeah. So that's maybe what makes it a little bit more complicated at the end. There's also questions of efficiency, which maybe we didn't get into, but that's a.
very well. So it seems like plenty of additional opportunities in the upcoming days to ask all the questions that will still pop up. Do you have an office here?
I think I can hang out in the guest office. I won't be here tomorrow, but today until 6, I think it's a good opportunity if you have immediate questions.
So there are several ways of getting in touch.
Or you can just write me an email too.
Exactly.
Yeah.
An email. He will be here until Friday.
Friday, yeah.
Super. Thanks
Okay.
again.
Okay, thanks.